The title of this presentation is Solving Feed-Forward PDEs with the Quantum Singular Value Transformation. To begin with a presentation overview, we'll be introducing the Quantum Singular Value Transformation, which is one particular transformation from the quantum algorithms and quantum physics literature, which can be used for several different purposes. And we'll be highlighting one of the purposes, which is the ability to solve feed-forward differential or partial differential equations. And in doing this and having to introduce this transformation, we'll be discussing and motivating how it is possible to make use of quantum computing for establishing comparisons with solving PDEs by classical methods, and the proposed speed up, or if there's even any speed up at all, for making use of this singular value transformation for solving PDEs. And after having determined the transformation and its connection with Hamiltonians and time-evolving Hamiltonians, we'll apply the transformation to create solution states for 8 partial differential equations. And we'll be sketching how the singular value transformation is very similar for a certain class of a couple of partial differential equations at the same time, and then draw the viewer's attention to the ability to be able to apply the singular value transformation, or what we'll abbreviate as the QSVT, quantum singular value transformation, for solving other partial differential equations, which are of a very similar form. And this is to say that there's the content and present in this presentation as a whole, it has connections with the other presentations that I've done on the channel, in which in one of the presentations I talked about how one can make use of resources in the cloud and cloud computing, and to even be able to access quantum hardware, which can allow us to determine how these algorithms would fare and perform on noisy intermediate scale devices in the NISQ era, is what people in quantum computing call it, as well as being able to apply this quantum algorithm, which is a variational quantum algorithm, which is a little bit different from the quantum singular value transformation because it's a gate-based quantum algorithm instead of a Hamiltonian-based quantum algorithm that we'll be describing, in which we can also look to solve to obtain solutions and numerically solve for partial differential equations which are involved in biological transport. And in the third, fourth, and fifth talk, I looked at connections and discussed connections with the variational quantum eigensolver, as well as talking about solutions to the Kamasa-Holm partial differential equation, which is a third-order partial differential equation that has a lot of nonlinearities, which are highly non-trivial, which the algorithm is able to study and time evolve forward for obtaining approximate numerical solutions, as well as the first talk that I gave in the APS April 2022 meeting, in which I was just testing out some things more and discussing how different components of the algorithm, such as the optimizer pool, and looking at how different optimizers and would fare numerically, and be able to help us test out whether this algorithm could work on some easier partial differential equations before scaling them up to more difficult ones. So we want to discuss and make use of the quantum singular value transformation for obtaining solutions to partial differential equations with a different type of quantum algorithm, which is along the lines of the motivation from the previous 5 talks that I was describing in the previous slide. And first of all, we have to make use of a unitary transformation. Unitary transformations, they appear all throughout quantum computing and quantum physics because they're used to time-evolve solution states which are initially set to the 0 state, in their time evolve forward in time, from which we would like to obtain some type of readout for the state, which can be used to reconstruct some components of the solution to the partial differential equation, or solutions to other types of problems that we can apply quantum algorithms to. And for this case, to begin introducing the quantum singular value transformation, we're looking at a unitary of this form, is in which if we fix some matrix A, where A can be a rectangular matrix or it could be a square matrix, we're constructing a unitary by looking at by a 2x2 matrix with the following off-diagonal and on-diagonal elements. For the on-diagonal elements, we have 2 very similar elements along the first and second entry of the diagonal, namely the square root of the identity operator of 1 minus some function evaluated at the Hermitian or the conjugate transpose of the matrix times f of a, namely the function evaluated at the matrix. And then for the other term of the matrix on the diagonal, it's minus square root of I minus f of A times f of the Hermitian conjugate of the matrix, as well as the off-diagonal elements being f of A dagger and f of A. So we're going to make use of this unitary because we're going to have to make some type of connection between a Hamiltonian, two Hamiltonians, in fact, in determining how we can construct a solution state for first order partial differential equations or first order differential equations that we can apply that we can make use of or that we can solve with the quantum singular value transformation. And the Hamiltonians that we're going to be used are defined in terms of the matrix A that we take. So again, whether this matrix is a rectangular or square doesn't matter, but we have to define one Hamiltonian, which is given by Z, which is 0 along the diagonal of the matrix, as well as on the anti-diagonal matrix, we have the Hermitian, the conjugate transpose of A and A itself, as well as the other Hamiltonian, which is very similar to the first Hamiltonian Z, with the fact that the entries along the diagonal can be arbitrary instead of having to be 0. And we also can characterize the eigenvalues and eigenvectors of the Hamiltonian. So this Hamiltonian lives in Hilbert space. So we can form an eigenvalue equation, eigenvalue system, in fact, which consists of two equations, namely the first entry of the vector that the Hamiltonian acts upon is the right eigenvector, and then the second entry is plus or minus the left eigenvector. And this Hamiltonian acting on these two states for the right and left eigenvectors is equivalent to plus or minus sigma j, the eigenvalue, times the same vector, which is given by the right eigenvalue and plus or minus the left eigenvalue. And we also can characterize the eigenvalues and eigenvectors of the unitary transformation that we had introduced earlier, which we had defined as a 2x2 matrix that's parameterized in terms of a function in whatever matrix A we're looking at. So the thing is that the unitary transformation acts on a state of psi as well as a 0 state, which is equivalent to an imaginary prefactor times the square root of I, the identity operator, minus the Hermitian conjugate of A times the Hermitian conjugate transpose of A times A, which acts on psi, as well as A up psi. So we're also defining an eigenvalue eigenvector relation in terms of the matrix A that we're looking at and some quantum state psi, which is going to be related to the solution state of the partial differential equation or differential equation that we're interested in solving. And as we've been saying and alluding to and discussing, the quantum singular value transform takes the following input. So it takes as input a matrix and the initial solution state. So A is the matrix, boldface I is the identity operator, and psi is the initial solution state for the differential equation that we're interested in solving. And what we're going to do is we're going to start the time evolution from this initial state, which is given by the first entry of the row vector. And we're going to be time evolving the solution state forward, given some fixed increment of time, by multiplying the solution state by A, which is the matrix. And then we're going to iterate this process for n-1 entries of the row vector to obtain A, which is the matrix raised to the n-1 power, which is the n-1th entry of the row vector, which is also multiplied by square root of the identity of I minus the Hermitian conjugate transpose of A times A. And the final state at time step n of the solution to the partial differential equation that we're interested in solving with the QSVT is A to the n times psi. And this row vector can also be expressed in the following summation, in which we have a summation over n-1 terms, and then we have a summation, and then we have just one term left over that's for the nth term, which is excluded from the n-1 terms of the summation. So in the summation from of k from 0 to n-1, we're taking a summation of the following quantum state, which again it's equal to square root of the identity minus A dagger times A raised to the kth power times the solution state of psi times another quantum state for k, where k is varying. K is just the index, the index of the summation, and then the nth term that we have is A to the n of psi times the quantum state for n. So this is just giving an exact expression in a relation for how one can obtain the solution of some feed-forward differential equation or partial differential equation in terms of taking the summation over n minus 1 terms of this row vector and then adding on an nth term, which represents the value of the solution state that we obtain by time evolving the Hamiltonians at time step n of the time evolution that we're performing. And we can apply the quantum singular value transformation to the following feed-forward partial differential equations. We can look at the heat equation, the reaction diffusion equation, the heat kernel equation, the Cole-Hopf transformation equation, as well as the Hartree equation and the Mason-Weaver equations. And a lot of these partial differential equations, they have very similar quantities that can be used for A and B, where B is another quantity that we're going to introduce, which is related to the structure of whatever partial differential equation or differential equation we're interested in solving. And this B quantity can be related to the A quantity, which is given from the summation over the n minus 1 terms and the nth term that we're looking at from the quantum singular value transformation. And for the three PDEs that we've been mentioning and alluding to, writing down the QSVT is almost the same. And this just stems from the fact that a lot of these partial differential equations, the underlying structure and statement of the partial differential equations is almost identical. So these partial differential equations, they admit very similar operators for the Hamiltonians, and they admit very similar relations for the way that the row vector of quantum states can be expressed as a summation over n minus 1 terms that we can use to obtain the desired solution state for some partial differential equation. So we have the heat equation, the heat kernel equation, and the Cole-Hopf transformation, which are all given by Laplacian of the solution of whatever the partial differential equation is. And we can look at the quantum singular value transformation for the heat equation, which is given by the Laplacian term for the B operator, from which we can obtain an A operator by taking whatever the B operator is, which is in this case the Laplacian, and multiplying it by the increment of time and adding that identity operator to it. So whatever the B operator is for the partial differential equation of interest that one wants to use to solve for the solution with the QSVT, one can obtain the A operator from this equality. And from A and B, we can write the QSVT with the following summation. So we're just taking and replacing all of the values of A with the value of the A operator that we obtained for the heat equation. And then we can express this summation by substituting A of HE, namely the operator for A that we obtained from the heat equation, from each one of the quantities that appears in each one of the entries for the solution state for the partial differential equation that we want to solve with the QSVT in each one of the entries of the row vector. And the final step is to convert the row vector into a summation of quantum states, which involves the A operator, which we have presented the general form of earlier in the slide. And this is just to say that the summation over A is given by this quantity, in which we have the first part, which is a summation over n minus 1 terms, as well as the second part, which is just the nth term. And this is just a special case of the general relation, with the exception that we make use of and substitute the value of the A operator for the heat equation in all terms where A appears in the summation over K for n minus 1 terms, as well as the last nth term. And one can follow the same procedure to apply the QSVT to other PDEs of a similar form, namely taking this summation over n minus 1 terms in the nth term and looking at what would the value or what would the expression for the A operator be for other partial differential equations, and forming a summation for any partial differential equation or differential equation that we're interested in solving, given that it satisfies a particular form of being a first order partial differential equation in which the time derivative of the solution state for the quantum solution state that we're using to approximate the solutions at different time steps of the evolution is equal to B times the solution state itself. So conclusions that we want to close out the presentation with is that we introduce the QSVT and we describe how time evolution of two Hamiltonians is related to constructing the desired solution state. And we establish an equivalence of the quantum transformation for obtaining numerical solutions of the heat equation, the reaction diffusion equation, the heat kernel, and the Kohl-Hopf transformation, as well as being able to apply the same transformation to obtain numerical approximations of solution states of other partial differential equations. And we describe how the summation over A operators, which we obtained from the row vector, is related to this row vector of quantum states that we described in detail, how we obtain the first entry and the last entry of this row vector of the solution states, and how we can time evolve each one of the states in between to obtain intermediate entries of the row vector, which are representing different values of the solution state throughout the time evolution. And thanks for listening.